Hi everybody, Cal here with section 16.5, Curl and Divergence, and section 16.6, Parametric Surfaces and Their Areas. We're going to start here in 16.5. Two operations on vector fields that we're going to define in this section. One is called curl, and the other is called divergence. The first is curl. It's very formulaic. The curl of f is, well, this thing written here, and you're never going to remember this formula the way it's presented. So the way to calculate curl is to think of curl of f as del cross f, okay, where del is your gradient operator, okay? And this really works up here by sticking, as though you're doing a cross product, I, j, k on top, your del, d dx, d dy, d dz in the middle, and then your f, p, q, r on the bottom. And then when you take that determinant of the 3x3 matrix, you end up with the formula for the curl of f. This is the safe way to remember the formula. So you really want to think of the curl of f as del cross f. Going forward, we have an example of calculating the curl. Now we have this theorem. If f is a function of three variables has continuous second-order partial derivatives, then the curl of the gradient of f is 0. So curl of a gradient function is 0. And this just comes from plugging and chugging. The proof is something you should be able to follow. So remember, curl of a gradient is 0. That means that if f is a conservative vector field, its curl is 0. This is one way of identifying when a vector field is or is not conservative, is by taking its curl and seeing whether or not it's 0. And example 2 shows that in action. Theorem 4 says what I just said. If we have a vector field whose curl is 0, then it is conservative. So this is like a theorem that we had in section 16.3. We had if dp dy minus dq dx is equal to 0, then f is conservative. That's for a two-dimensional vector field. This is the same thing, but in 3 dimensions. And in fact, you'll notice that if we, well, I'll talk about this in class, but that previous theorem is a special case of this one. Example 3 again shows this in action. So, and part B, by the way, is also worth looking at here. So, then we get into, your book talks a little bit about the meaning of curl, and we'll talk about that in class, but do give this a quick read. Then we get into divergence, and if curl is del cross f, divergence is del dot f. This is dot product. This is d dx, d dy, d dz dot p, q, r. And you can see this happening here. Curl takes in a vector field and spits out a vector field, and this is actually specifically a vector field in R3. Div spits out a scalar function, a scalar field. Okay? And example 4 shows computation of divergence. Theorem 11 says that the div of the curl of a vector field is 0. So curl of a gradient is 0, div of the curl is 0. And that's fairly interesting. Example 5 shows working with that theorem. And then we get into the idea of what divergence means. And again, I'll talk about that in class, but you can read this here. I would not pay a heck of a lot of attention to this Laplace operator stuff at the bottom of page 1119. Then we get into vector forms of Green's theorem. This is just some notational work with Green's theorem. Read through it. This should hopefully make sense, especially square 12 over here. And you can understand Green's theorem also in terms of 13 here. But this is not like hugely important. This is not going to change your life or anything like that. But do read these. Make sure you understand the two squares in that section. So that's 16.5. Let's move straight on to 16.6, which is parametric surfaces and their areas. So just like we've talked about parametric curves before, here we're going to talk about parametric surfaces. If it takes one variable to parameterize a curve, it takes two variables to parameterize a surface. And we're going to have just some examples of parametric surfaces for the first part of this section. So example 1 gives a really common parameterization of a cylinder. And let's see, your book talks a little bit about grid curves, which are kind of like traces. In fact, they more or less are traces on your parametric surface. I would ignore using a computer algebra system to graph a surface. We're not going to worry about that. You may, however, want to think about example 3. This is a pretty good example, finding a vector function that represents the plane passing through a point with a certain position vector containing two non-parallel vectors a and b. Easy way to get a parametric representation of a plane. And finding a parametric representation of a sphere should be pretty straightforward. We're using spherical coordinates to do it. Examples 5, 6, 7 are all pretty stock sorts of things, finding parametric representations for pretty stock examples. And your book also talks about surfaces of revolution. You can kind of see circles, cosine theta, sine theta showing up in there. So make sure you understand what's going on in example 8. It also goes through parameterizations of tangent planes, which should be familiar. And example 9 shows that in action. Finally, we get into surface area, which says, once you have a parameterization of a surface, how do you find the surface area? And your book comes up to a couple of formulas here, and we'll get into why those formulas work. You could read the blurb before to see why it works. And example 10 shows that in action. And then we get into surface area of the graph of a function, which just uses those previous formulas for the setting of having a function of x and y. And so you get this nice formula here, and this formula should not be a shock. Example 11 shows it in action. And I'm going to say you can kind of skip that last page of the after the example. So that ties together 16.6.